The main objective of having an inspection is to supervise that the safety level is maintained, and then you can do more or less all types of inspections. It's also the principles ones are telling you when to start activities, including special inspections. And it's a way of planning ahead on what to do on your structures. Again, one challenge in the traditional way of doing these inspections is it does not take hidden degradations into account. You can have, if you base your inspections and your maintenance and operations on visual inspections, it prevents you from doing a preventive maintenance strategy, which by logic you need to do before your deterioration has onset to a significant level. When you have your investigation, the objective, in my view, is threefold. One is that we need to know what the deterioration mechanism is. Often that is as documentation, because very often we can look at the structure and have a very good idea on what caused the deterioration, but sometimes we are surprised. It's also what the deterioration extent is. If you want to plan for a repair job, you need to know what the extent of deterioration is, otherwise you cannot quantify your project adequately. Last but not least, the rate at which your deterioration takes place. If it is in such a slow rate, you may want to postpone your repair works. That might be cost optimum for you. More advanced testers should always have specific purposes. What caused the cracking? Are they significantly, you can do statistic plans on testing, but very often they would not be economic to perform. So it's very often is a selected testing that you do, planning ahead. There are a lot of different test methods that you can apply to structures, and you say, which one should I select out of these? Yes, that depends very much on what you want to do with your testing. We normally say that in order to get a good overview, visual inspections or investigations are very, very strong tool in doing so. But that would only give you a little insight in what caused your problems. Based on this, you can put forward hypotheses on your deterioration mechanisms, but you need to detail your testings and maybe down to even scanning to know exactly what caused your problems. So potential mapping, impulse response testing systems, they are good also at giving overview and extension deterioration. But then we go down to corrosion rate, which is deterioration rate, and also finding causes on your problems. So visual inspections, you need to know, you need to map where you have your deterioration and to what extent. We always bring a hammer on site, which is extremely good in detecting where you have flaws in the concrete cover zone, that is, because if you have deep defects, deep delaminations, it will not be able to detect those. You need also, in some cases, to clean your structure to know what you're looking at. Maybe there are some cracks that are not visible. That goes in particular also when you talk about below water. Below water you always have to clean your structures. You can look in more depth, what is your crack width, and you all got one of those. It has also US units on it.
That's pretty good.
Yes, it is actually quite good. And you can use hammers, and you want to or even chains on deck if you don't have a membrane on top of it, and you limit where you have your direct deteriorations, very often corrosion. Non-destructive testings. Cover meter is a very simple tool to measure both the concrete depth, very often also the reinforcement diameter. So you can use it to look at compare it to the as-built drawings. In some cases you cannot use cover meters if you have a very high steel density, very narrowly spaced reinforcement bars, then your cover meter will not be able to distinguish between them. Also, most cover meters, they work by induction. So if your steel is not magnetic, like most stainless steels are not magnetic, so you cannot use cover meters in that situation. But cover is of course of significance if you have a very large variation. It would have a large input on your structure service life. Could look like this one, a perfometer. This one, you stroll down your concrete surface and you get a map where you have your entire cover meters. This is actually an example from a balcony I took, but you can significantly see here you have between 0 and 20 millimeters, and out here it's more according to what it should be. Half-cell potential mapping or testing. We do that on most structures where we can do it. However, on epoxy coated rebars, where we're working together with some of our colleagues up north, that is not a way ahead because there's not continuity. It has to have continuity between the rebars in order to be a reliable method. It's fairly simple. The data logging thing is probably the more advanced of it. We measure potentials and we also measure resistance between the steel and the reference electrode, which is a good measure as a supportive evaluating tools. It's used to indicate the risk of corrosion. It does not tell whether we have corrosion. So for this reason, it always has to be calibrated, your results. You do a mapping of it, and then you select different areas where you go and check what the steel looks like in itself. There is an ASTM specification, C876, that has been based on American bridges with no membranes on top and being de-iced. They have values for low, indeterminate and high probability of corrosion, but as many structures are not directly comparable to that, calibration is always required. This is an example on a mapping with half-cell potentials. It's from a bridge abutment, and you have here a cast joint. The more negative your potentials, the higher risk of corrosion. However, very low negative potential can also be areas where you do not have a lot of oxygen. So that's also a reason why you should calibrate your results. You then have you'll check where you are on certain. You have to confirm that you have corrosion where you expect it, but you also have to limit the extent in corrosion by testing also where you have a value which is an uncertain corrosion. It's a very strong tool. We normally combine it with sampling for chloride, so you can connect or combine results from different testings in your evaluation. The next step forward would be corrosion rate measurements, where you can actually, by measuring, see if you have active corrosion taking place or if the steel is in a passive state. It's linear polarization methods or galvanostatic measurements. It's the same, more or less the same principle, even though this is the equipment that we use. You still have a reference electrode in the center of this. Then you have a steel circle here, and you apply a current to your steel. You have a guard ring so that you center the current that you have, and then you measure the response from this steel to the current that you apply. If you have a potential which significantly responds, then it's in a passive state. If it more or less swallows the current that you apply to it, it's in an active corroding state, and that can be calculated. Another equipment which is very usable in our view is thermography. So it's a simple camera, but with quite a high accuracy, down to 0.1 degrees Celsius. So it's high accuracy. The basic principle is that if you have a delamination or cracks in your structure, and you have ambient temperatures, the heating and cooling in those areas where delaminations will be at a different rate compared to neighboring areas. So you're looking for differences in temperatures when you're looking at these results. You should use this method at times where there's a change in temperature. That means early morning, late evening, where you have a change in this. And then you can go and detect smaller or large areas where you have a significant change in temperature in your structure, and you can then evaluate that could be a potential delaminated area. We normally record both the thermography picture together, that's what the camera does, together with what it looks like in real life.
So do you typically use this before you go with the hammer? This would give you
on some structures you cannot go with a hammer up unless you have a lot of scaffolding, so it's a combined thing. Yeah. Another very strong method, in my view, for detecting cracks, but also hidden degradations, is impulse response method. It's an acoustic method. It's for delamination in concrete structures, voidings, honeycombings, any debondings on any structures. And what you have is, this is a bridge deck. You have a hammer with a built-in load cell, and you have a geophone that will pick up the signals that you have on your structure. So and then you have a data logger connected to it. So you have a hammer impact, and you have the response on your geophone. You then do an FFT analysis, and you calculate a velocity over force spectrum. You get then a response signal, and you have different things where you can evaluate the results in these. These out here, it's called the mobility, and this is called mobility slope, for instance. There are different parameters that could be calculated.
So you use one geophone, or you use an array of geophones?
One geophone, hammer tapping, move to next area, hammer tapping, and pick up signals from
and
that.
So then the signal that you get would only be at that geophone location,
yes.
Right?
Yes.
It would not be or do you also consider the path between the hammer and the geophone?
They are normally just
closely
next to each other, as practically as possible. I have this example, which is, I think, a very good example on how to use this method and how you can benefit from it. These are two twin bridges where the load carrying capacity had to be verified because they wanted to upgrade the load on those two bridges. By visual inspection, the bridge deck looked fine. There were no signs of visual damages or defects on it. We used the impulse response, and we got a number of plots. What you saw before with the mobility and mobility slope is represented by individual points here. So this is one area which was measured, and we had several of those along the two bridges. Normally we say that if we have a mobility slope which exceeds 3, that can indicate a poor compaction resulting in flaws and defects. Mind you, we had no visual signs that we had anything. You could use a hammer, you could not hear any defects in this. But all of our results indicated that we had considerable problems with structural integrity. We then selected we selected 13 locations for core drilling, both in areas where we expected no defects and in areas where we did expect defects. Some of the cores even came out like this. And some of the cores we had cracks in different depths.
How well the thermal imaging versus geophone compare with each other?